Welcome in. Our goal for this video is to describe the relationship between pressure, volume, temperature, and moles of our gases using what we call gas laws. We introduced our four properties of our gas: pressure, volume, moles, and temperature. Our simplest gas laws are going to be only looking at 2 or 3 of these properties at a time. When we're examining these trends, we want to think about what that trend is. And since we're talking about laws, we can derive some useful equations. We can also use our kinetic molecular theory from our previous lesson to explain why these are true. We can start with what we call Boyle's law. This is examining only the pressure and volume of our gas, leaving everything else as a constant. We have a picture of what this looks like. We can measure the volume of our gas. Here we have 1 liter of our gas. And we can measure the pressure of our gas. Here we have 1 atm worth of pressure. If you compress this gas, change its volume, we are going to have to change the pressure of our gas as well. Our observation is that these are inversely proportional. As one gets bigger, the other has to get smaller. These are going to be the opposite trend. If you decrease the volume, we can measure that the pressure has to increase. If we have something inversely proportional, we can write this relationship. The alpha sign means proportional, and the fact that we have a fraction on the right side means inversely proportional. That proportional symbol we can replace with an equal sign if we also put in a multiplication constant. This is what it means to be proportional. Equal to it, but you have to multiply by some number. Our math trick is we want to try to isolate that constant because that will give us some interesting information. What we find is that our pressure times our volume has to be a constant in this situation. This is really cool, actually. If we take our pressure and multiply it by our volume, it equals some number, and that number is not going to change. If you change your pressure, your volume is going to change as well, or if you change your volume, your pressure is going to change as well, but they'll still multiply together to equal that same number, that same constant. What we end up with is a nice useful equation. Our P1V1 equals P2V2. The initial pressure times the initial volume has to be equal to our final pressure and our final volume. We said we want to know the trend, and we want to know that useful equation. We also want to know why this is the case. We can use our kinetic molecular theory to give a logical explanation for why. In this situation, we are only changing the pressure and the volume, which means that the amount of our gas and the temperature are not changing. The temperature tells you the speed of your gas particles, and we know that our speed has to be unchanged. Our temperature is unchanged. If we choose to decrease the volume, then we'll have more collisions, and more collisions means we have more pressure. Therefore, volume and pressure have to have that opposite trend. We can do an example of a calculation problem we might see. The first one says, calculate the pressure of a gas that was initially at 765 millimeters of mercury and 1.78 liters, but was compressed to 1.25 liters. We can start with the equation here. We're only changing pressure and volume, so we get to use this P1V1 equals P2V2 equation. Then we can fill in the values that we know, our initial pressure and our initial volume, and our final volume. For units here, it doesn't matter the units we use as long as they match up on both sides. So our answer will be in millimeters of mercury, which is totally fine. We have another problem here. Let's do this one for practice. So pause the video, grab some paper, calculate a good answer. We can move on to our second simple gas law. Now we're looking at volume compared to temperature. If we're changing only the volume and the temperature, we can leave the pressure and the amount of gas the same, and we can make some observations. What we see is if you increase the temperature of your gas, the volume has to increase as well. We call this directly proportional. We can have this same trend. If one of them increases, the other increases as well. Again, we can derive an equation. It looks a little bit different here because our trend is directly proportional instead of inversely proportional. The idea is the same. You can set up an equation with a constant on one side and use that to give you some nice information. The volume divided by the temperature has to be the same number no matter what under these constant pressure and moles conditions. This is our nice equation to remember, as well as our trend. Again, we can try to understand why this is the case, give some good logic here. Well, we have constant pressure under this situation, which means that pressure is not changing. Pressure here is a constant, and therefore our number of collisions is not changing. If the temperature increases, then the speed of our gas is increasing as well. But how can we make sure that the speed of our gas is increasing while still not increasing the number of collisions? This seems like it's hard to do unless we're allowed to change our volume, increase that volume to allow more room for our gases to be bouncing around at that faster speed. So our trend here, if our temperature is increasing while keeping the pressure constant, we need to increase the volume as well. This is the only way for our pressure to not increase. We have some more calculation style questions to practice with. Suppose we have 2.37 liters of our gas at 295 Kelvin. It's heated to 354 Kelvin. The only things changing seem like they are volume and temperature. So we can use our nice Charles's law equation. We're trying to solve for volume. I'm going to do the algebra first and then fill in our numbers from there. Again, our note about units, make sure that your units match up on both sides, and be careful, temperature has to always be in Kelvin. These Kelvin units are vital for doing our calculations that involve temperature. Otherwise, these equations simply do not work. We have another question here for practice. Again, try to grab some pencil and paper, write down some good answers, and be careful. We need to convert our Celsius into Kelvin instead so that this is something that it is possible to calculate. We can combine our first two gas relationships into a third combined relationship. This is known as the combined gas law. Volume is related to both temperature and pressure. If we're changing all three of these at once, we can put our two equations together. P1 V1 divided by T1 is equal to P2 V2 divided by T2. Here's an example of what these calculation questions might look like. We're carrying a cylinder with a movable piston. Our volume is initially this, our pressure is initially this, and the temperature is initially this. At the end, our pressure has changed, our temperature has changed. We want to figure out the volume. Since we have all three variables changing, we can set up our combined gas law equation. You can either plug in the numbers and do some algebra, or you can do some algebra then plug in the numbers. I'm going to do that second option, but both are totally fine. Again, our units need to match up on both sides, and our temperature always in Kelvin, which thankfully it is to begin with. No conversion necessary to begin. We end up with our final answer. Our volume has changed. It is slightly larger, 3.87 liters. Again, we have a practice problem for you to do. So go ahead, pause that video, try to calculate a good answer. Our next simple gas law starts to involve our last property of gases, moles. Our observation is that when we increase the amount of gas, the volume also increases, assuming that we are not changing the temperature or pressure. This is known as Avogadro's law, our same Avogadro. And the trend here is that these are directly proportional. If you change your volume, your moles is also going to change in that same direction. Just as before, we can get our useful equation. Here we have V1 divided by N1 is equal to V2 divided by N2. For practice, try to decide why this is the case using our kinetic molecular theory. Here's an example of a practice calculation problem using Avogadro's law. Here we are changing just our volume and our moles. We know our new volume. We want to figure out how many additional moles were added. Again, I like to do the algebra first before plugging in the numbers. When we run these numbers, we find that our final amount of moles has to be 0.29. Be careful. Our question is asking how many additional moles. This is going to be the total amount. We need to do one extra subtraction step to decide how many moles to add in order to reach our final amount. All right, it's time to put everything together. We can relate all four of our gas properties using what we call the ideal gas law. The pressure times the volume is equal to the moles times R times the temperature. This R is known as the ideal gas constant, and it's just a number. We're going to use R in these units, 0.0821 liters times ATMs divided by moles and kelvins. But our tip here on this slide is a way to not have to memorize all of those simple gas equations. Instead, we can use this ideal gas law. If we rearrange it so that R is all the way by itself, this is now that same derivation we had for our simple gas laws, but using all four properties. Once we have this set up, we can identify any of the properties of our gases and use this equation to find that simpler P1V1 equation or V1N1 equation, etc. For example, if we want to know the relationship between pressure and volume, we can set up R is equal to PV divided by NT, and then look where pressure and volume are. Oh, they're both next to each other. That means they need to be next to each other in our simple gas equations. If we want to look at volume and temperature, again, we can look at that setup for our ideal gas equation. Volume and temperature are on top of each other, and so in our equation, we also need to have that trend. Here's one we might not have talked about. If you want to compare pressure and temperature, those two variables are on top of each other also. And so we can have this equation, P1 divided by T1 is P2 divided by T2. Once more, we have a practice question for you to try. Grab that paper, try to calculate your best answer. All right, our last type of calculation that we can use, the ideal gas law, is an equation itself. We are going to know that value of R, the ideal gas constant. That means if we measure any three of these properties, we can calculate the fourth one. Our simple gas laws with the 1s and 2s on each side, that's good if we are changing something about our gas. This ideal gas law is good if we are not changing anything about our gas. A note on units, before the units didn't matter that much, but now we need to make sure all of those units are the same as in our ideal gas constant. One last practice problem for you to complete. Again, grab that paper, pause the video, try to get your best answer. And there we go, we've done it. We can describe the relationship between any of our pressure, volume, temperature, and moles of our gas using our simple gas laws and what we call that ideal gas law. Well, there we go. Thanks so much for tuning in. Hope you all have a great day, and I will catch you next time.